The universe just whispered a secret, and scientists are scrambling to decode it. Earlier this year, a team analyzing data from the James Webb Space Telescope spotted something extraordinary: chemical signatures in a distant exoplanet's atmosphere that shouldn't exist naturally. This isn't science fiction anymore. Right now, as you watch this, 30 cosmic puzzles are being pieced together, each one a potential fingerprint of life beyond our world. From toxic clouds on Venus hiding possible microbial cities to oceans trapped beneath alien ice shells ripe for exploration, the evidence is stacking up in ways that would make even the most skeptical astronomer pause. Today, we're taking you on a journey through the most jaw-dropping discoveries, 30 reasons why we might not be alone in this vast cosmic neighborhood. Stick around, because by the end, you'll see the night sky in a whole new light. Now, let's zoom in on one of the most explosive discoveries in recent years, one that turned our gaze back to Earth's fiery twin, Venus. In 2020, a team of astronomers dropped a bombshell. They had detected phosphine gas in Venus's upper atmosphere. Why does that matter? On Earth, phosphine is almost exclusively linked to life produced by microbes in oxygen-free environments like swamps or even our own intestines. Finding it on Venus, where surface temperatures could melt lead and clouds are laced with sulfuric acid, was like stumbling upon a smoke signal in a volcano. Scientists were stunned and immediately divided. The detection suggested that high in Venus's toxic clouds, microbial life might be thriving, floating in droplets where temperatures and pressures are surprisingly Earth-like. But here's where things get messy. Critics argued that phosphine could be produced by unknown geological or chemical processes, though no known Venusian phenomenon neatly explains it. Follow-up studies have swung like a pendulum. Some teams confirmed the phosphine signal, while others claimed it was just sulfur dioxide masquerading as phosphine. The debate rages on, turning Venus into a cosmic courtroom where every new observation is another piece of evidence. What's next? This discovery has reignited interest in Venus like never before. NASA's upcoming Da Vinci mission will plunge through the planet's atmosphere, sniffing for gases like phosphine, while Europe's Envision orbiter will map mineral hotspots that could hint at hidden chemistry or biology. Even private initiatives are jumping in, with projects aiming to send balloon probes to float in those mysterious clouds. Here's the kicker: if life is hiding in Venus's skies, it reshapes everything we thought we knew about where life can survive. A planet once written off as a hellscape might just harbor the first proof we're not alone, and that's a revelation worth waiting for. But Venus isn't the only place sending us mixed signals. Up next, we're heading to Europa, where an entire ocean hides beneath its frozen crust, and the clues there are just as tantalizing. Moving beyond Venus, let's set our sights on a world that might just be the solar system's best bet for hosting life: Jupiter's enigmatic moon, Europa. At first glance, Europa's frozen, cracked surface looks inhospitable, but beneath that icy shell lies what scientists believe could be a vast, liquid ocean, one holding twice as much water as all of Earth's oceans combined. What makes Europa so special? For starters, Hubble Space Telescope observations have captured something extraordinary: towering plumes of water vapor erupting from the moon's surface like geysers shooting into space. These plumes suggest that Europa's ocean isn't just sitting there. It's active, possibly interacting with the surface and even venting nutrients into space. That's a game changer, because where there's liquid water, energy, and chemical building blocks, there's potential for life as we know it. Now, here's the real kicker: Europa's ocean doesn't freeze solid despite being so far from the sun. The secret lies in tidal heating. As Europa orbits Jupiter, the gas giant's immense gravity stretches and squeezes the moon, generating enough internal heat to keep that massive subsurface ocean liquid. It's like kneading dough. The friction creates warmth, turning Europa into a cosmic pressure cooker where life could simmer. But how do we get a closer look? Enter NASA Europa Clipper mission, set to launch in the coming years. This spacecraft won't land, but it'll perform dozens of close flybys using radar to peer through the ice, spectrometers to analyze surface chemistry, and high-resolution cameras to scout for fresh plume activity. If Europa's ocean is indeed venting into space, Clipper could even sample its contents without ever touching down, searching for organic molecules or other hints of biological processes. The implications are staggering. If Europa's ocean harbors life, it would prove that habitable zones aren't just about a planet's distance from its star. They could exist anywhere there's liquid water and energy, even in the frigid outer solar system. And if that's the case, imagine what other hidden oceans might be out there, waiting to be discovered. But Europa isn't the only moon with secrets. Next, we'll dive into another icy world where hydrothermal vents and organic molecules are rewriting the rules of where life might thrive. Now, let's journey deeper into the outer solar system to Saturn's dazzling moon, Enceladus, a tiny, ice-covered world with a massive secret. While Europa's ocean has captured headlines, Enceladus might just be the most surprising contender in the search for extraterrestrial life. Unlike Europa, where we infer the ocean's existence from plumes and surface cracks, Enceladus boldly sprays its subsurface secrets straight into space, giving scientists a free sample of what lies beneath. When NASA Cassini spacecraft first spotted geysers erupting from Enceladus's south pole, it was a jaw-dropping moment. These weren't just ordinary plumes, they were massive jets of water vapor, ice particles, and even organic molecules blasting hundreds of kilometers above the surface. Cassini didn't just observe them from a distance, it flew right through these plumes, analyzing their composition in real time. What it found was astonishing: salts, silica nanoparticles, and complex carbon-based compounds, all ingredients that, on Earth, point to hydrothermal activity deep in the ocean floor. Here's where things get even more exciting. The silica particles Cassini detected are nearly identical to those produced by hydrothermal vents on Earth, where scorching water reacts with rock to create energy-rich environments. On our planet, these vents teem with life bacteria, tube worms, and entire ecosystems thriving in total darkness, fueled by chemistry rather than sunlight. If Enceladus has similar vents, as the evidence strongly suggests, it could be doing the same thing, brewing the perfect conditions for life in its hidden ocean. But how does a moon barely 500 kilometers wide, smaller than the length of the United Kingdom, maintain such a dynamic system? Like Europa, Enceladus owes its activity to tidal heating. Saturn's gravitational pull stretches and flexes the moon, generating enough internal heat to keep its subsurface ocean liquid and power those dramatic geysers. The difference: Enceladus's ocean is in direct contact with its rocky core, allowing mineral-rich water to cycle through hydrothermal systems, a critical factor for life as we know it. The implications are profound. Enceladus isn't just a passive ice ball. It's a geologically active world with a global ocean, energy sources, and organic chemistry. That trifecta makes it one of the most promising places to search for life beyond Earth. And while Cassini's mission ended in 2017 by plunging into Saturn's atmosphere, its data continues to inspire. Proposed missions like NASA Enceladus Orbiter aim to return with advanced instruments, possibly even a lander that could touch down near those plumes to search for direct evidence of biological activity. What makes Enceladus especially tantalizing is accessibility. Unlike Europa, whose thick ice shell might require drilling, Enceladus generously ejects its ocean material into space. Future missions could simply fly through the plumes, capturing samples to analyze for amino acids or other biosignatures. No digging required. If life exists there, we might not need to look far to find it. So, while Europa gets much of the spotlight, Enceladus quietly steals the show with its explosive plumes and Earth-like chemistry. It's a reminder that life might not need a sunlit paradise, just water, energy, and the right mix of elements even in the coldest corners of the cosmos. And speaking of cosmic chemistry, our next discovery takes us from icy moons to the dusty surface of Mars, where mysterious methane spikes have scientists debating the ultimate question: is something or someone making this gas? Shifting our gaze from the icy plumes of Enceladus, we land on the dusty, rust-colored terrain of Mars, a world that's been teasing us with one of the most puzzling clues in the search for life: mysterious bursts of methane. Unlike the steady, predictable methane sources on Earth, Mars delivers this gas in erratic spikes, leaving scientists scratching their heads. Is it a sign of hidden microbial activity, or just the quirks of a geologically active planet? Let's unpack this cosmic whodunit. Since its landing in 2012, NASA Curiosity rover has been sniffing Martian air for traces of methane, a gas that, on Earth, is overwhelmingly produced by living organisms. Over the years, it's detected fleeting surges, some as high as 21 parts per billion. That might sound minuscule, but for a planet assumed to be chemically stagnant, these spikes are staggering. The plot thickens when you realize these detections aren't consistent. Methane appears and vanishes unpredictably, sometimes spiking at night or Chinese letter seasons. It's as if Mars is playing a game of peekaboo with us. So, where's the methane coming from? The biological explanation is tantalizing. On Earth, microbes called methanogens thrive in oxygen-free environments like swamps or animal guts, belching methane as a byproduct. If similar microbes exist underground on Mars, perhaps sheltered from radiation in briny aquifers, they could be producing these sporadic puffs. The idea isn't as far-fetched as it sounds. Methanogens are ancient life forms capable of surviving extreme conditions. If life ever took hold on Mars, these hardy organisms might be the last holdouts. But before we jump to aliens, let's consider the non-biological contenders. Methane can also form through geological processes like serpentinization, a reaction between water, carbon dioxide, and certain rocks like olivine, which Mars has in abundance. Solar ultraviolet light breaking down organic debris on the surface could also release methane. Even more intriguing is the possibility of ancient methane trapped in ice clathrates, occasionally leaking out when temperatures shift. These explanations are compelling, but they don't fully account for the gas's erratic behavior. If geology were the sole culprit, we'd expect steadier, more predictable emissions. Enter the mystery of methane's disappearance. ESA's Trace Gas Orbiter, designed specifically to study Martian atmospheric gases, has repeatedly failed to confirm Curiosity's ground-level detections from orbit. This discrepancy has spawned theories. Maybe methane is destroyed near the surface by reactive salts or ultraviolet light before it can reach the upper atmosphere. Or perhaps the releases are so localized and brief that orbiters simply miss them. It's a detective story with conflicting witness testimonies. This is where NASA's Perseverance rover comes in. Equipped with upgraded sensors, it's cross-checking Curiosity's findings while scouring Jezero crater for ancient signs of life. Future missions like the Mars Life Explorer could drill deeper to sample subsurface ice, hunting for microbes or their chemical traces. The stakes are high. If Mars methane is biological, it'd be the first evidence of life beyond Earth. Even if it's geological, it'd reveal a more dynamic Mars than we imagined, one with hidden water reserves or active chemistry that could one day support human colonists. For now, Mars keeps its secrets, but every erratic methane spike is a breadcrumb, drawing us closer to answering whether the red planet ever hosted or still hosts life. And as we ponder that, our next discovery catapults us light years away to a star system crammed with not one, not two, but 7 Earth-sized worlds all dancing in perfect harmony. Leaving the mysteries of Mars behind, let's venture into a star system that feels almost too perfect to be real. TRAPPIST-1, a cosmic jewel box holding not just one, but 7 Earth-sized planets, 3 of which sit snugly in the habitable zone. Imagine a solar system so compact that its outermost planet orbits closer to its star than Mercury does to our Sun. This ultra-cool dwarf star, barely larger than Jupiter, hosts a family of rocky worlds where a year passes in just a handful of Earth days. But what makes TRAPPIST-1 truly extraordinary isn't just the number of planets. It's the tantalizing possibility that some could harbor liquid water and perhaps the ingredients for life. Discovered in 2017, this system immediately rewrote the rules of planetary science. The 3 habitable zone worlds TRAPPIST-1e, F, and G are particularly intriguing. Their tight orbits might sound inhospitable, but because their star is so faint, they receive just enough warmth to potentially maintain liquid water without boiling or freezing. Picture a world where the sun hangs like a dim, ruby orb in the sky, casting perpetual twilight. Yet, tidal forces from their star could keep these planets geologically active, fueling subsurface oceans or even volcanism that might recycle nutrients, a key ingredient for life as we know it. But how do we study these distant worlds? Enter the James Webb Space Telescope, our most powerful eye in the sky. TRAPPIST-1 architecture is a gift to astronomers. The planets transit their star frequently, passing in front of it from our viewpoint. Each transit allows Webb to analyze starlight filtering through their atmospheres, hunting for biosignatures like oxygen, methane, or even industrial pollutants. Early observations have already ruled out thick, hydrogen-dominated atmospheres on some of the planets, suggesting they're more like Earth or Venus than gas giants. The next step, detecting water vapor or chemical imbalances that hint at biological activity. There's a catch, though. TRAPPIST-1 is a red dwarf, a type of star notorious for violent flares that could strip atmospheres or bathe planets in lethal radiation. Some models suggest the innermost worlds might be barren, their air lost to space, while others propose that magnetic fields or carbon-rich atmospheres could shield life. Even more intriguing is the idea of yo-yo habitability, a planets alternately scorched and frozen by their star's mood swings, yet still hosting life in subsurface refuges. The TRAPPIST-1 system isn't just a catalog of exoplanets, it's a laboratory for testing the limits of habitability. Whether these worlds are lush, sterile, or something in between, they're reshaping how we define a living planet. And as Webb peers deeper into their secrets, we edge closer to answering whether life is a cosmic fluke or a universal norm. Now, let's turn our attention to another world where water takes center stage, but in a form stranger than fiction. The Hycean planet K2-18b, where oceans might stretch across an entire globe under a crushing hydrogen sky. Shifting our gaze from the tightly packed TRAPPIST-1 system, we arrive at a world that defies expectations. K2-18b, a distant planet where the very definition of habitable is being rewritten. This isn't just another exoplanet, it's a Hycean world, a term coined by astronomers to describe a hot, water-rich planet shrouded in a thick hydrogen atmosphere. And thanks to the James Webb Space Telescope, we've caught glimpses of something extraordinary in its skies, water vapor, and whispers of a molecule that, on Earth, is almost exclusively produced by life. In 2023, Webb's razor-sharp instruments peered through the haze of K2-18b, located 120 light-years away in the constellation Leo. What they found sent shockwaves through the scientific community. Not only did the planet's atmosphere show clear signs of water vapor, a first for a world of this type, but there were also tantalizing hints of dimethyl sulfide, a compound that, on our planet, is churned out by marine phytoplankton. Could this be a flicker of alien biology or just a trick of chemistry? The debate is far from settled, but the mere possibility has turned K2-18b into a beacon of astrobiological hope. What makes this planet so revolutionary is its place in the habitable zone, the Goldilocks region around a star where temperatures might allow liquid water. But K2-18b is no Earth twin. It's a sub-Neptune nearly 9 times our planet's mass, with a steamy ocean that could span its entire surface beneath a smothering hydrogen envelope. Until recently, scientists assumed such worlds were too hostile for life, their crushing pressures and scalding temperatures ruling them out. Yet Hycean planets like this one are challenging those assumptions. Their vast oceans, warmed by internal heat or tidal forces, might harbor conditions suitable for extremophiles organisms akin to Earth's deep-sea vent dwellers. The key lies in the hydrogen-rich atmosphere. While it sounds suffocating, this gaseous blanket could act as a shield, trapping just enough heat to maintain liquid water without boiling it away. Meanwhile, the presence of dimethyl sulfide, if confirmed, would be staggering. On Earth, this molecule has no known non-biological source in appreciable quantities. Of course, alien chemistry might follow different rules, and follow-up observations are crucial to rule out geological or photochemical processes. But the implications are dizzying. A world where life might thrive not despite the extreme conditions, but because of them. K2-18b also forces us to rethink the boundaries of habitability. Traditional searches focused on Earth like rocky planets, but Hycean worlds expand the playing field. They're more common, easier to detect, and, if life can indeed persist in their global oceans, could outnumber conventional habitable planets by a wide margin. Future Webb observations aim to solidify the dimethyl sulfide detection and scout for other biosignatures like methane or carbon dioxide imbalances. Each new datum could inch us closer to answering whether life is a galactic anomaly or a near-inevitable outcome wherever water and energy meet. As we continue our cosmic tour, let's turn to an object that left scientists utterly baffled. A visitor from beyond our solar system whose strange behavior sparked wild theories, including the unthinkable, was Oumuamua, an alien spacecraft. Now, let's journey from the steamy oceans of K2-18b to a cosmic mystery that streaked through our solar system. A visitor so peculiar it sparked debates about whether we just witnessed our first brush with alien technology. In 2017, astronomers spotted an object unlike anything seen before. It wasn't from our solar system. It wasn't behaving like a typical asteroid or comet. Its name, Oumuamua, Hawaiian for scout, and its oddities began piling up the moment scientists trained their telescopes on it. First, its shape. Most space rocks are lumpy or round, but Oumuamua was cigar-shaped, estimated to be up to 10 times longer than it was wide. Then there was its speed. As it hurtled away from the sun, it didn't just coast under gravity's pull, it accelerated, as if pushed by an unseen force. Comets often speed up slightly due to icy material vaporizing off their surfaces, creating a natural thruster effect. But Oumuamua showed no visible coma or tail, the usual hallmarks of outgassing. This left researchers scrambling for explanations, and a few bold voices, like Harvard astrophysicist Avi Loeb, suggested the unthinkable. Could this be a piece of alien hardware, perhaps a solar sail or derelict probe? The scientific community quickly split. One camp argued for exotic natural origins, proposing that Oumuamua might be a fragment of a Pluto-like world, rich in nitrogen ice that vaporized invisibly, nudging it forward. Others pointed to hydrogen icebergs, theoretical chunks of solid hydrogen that could outgas without leaving traces visible to our instruments. Then there was the more mundane possibility. Maybe we just missed faint outgassing because Oumuamua was too small or too far away for our telescopes to catch the details. But here's the twist: even if Oumuamua wasn't artificial, its very existence hints at something profound. Before 2017, we had no confirmed interstellar visitors. Now, thanks to advances like the Vera Rubin Observatory's upcoming sky surveys, we might spot dozens in the coming years. Each one is a time capsule from another star system, carrying clues about how planets and comets form in alien environments. Future visitors could help us test wild theories like whether hydrogen icebergs are real, or if other solar systems eject shards of exotic ices we've never seen. The real lesson of Oumuamua isn't just about one strange object. It's about how little we truly know. When faced with the unknown, scientists must balance open-mindedness with skepticism, chasing down every lead while resisting the allure of easy answers. Whether it was a nitrogen shard, a hydrogen snowball, or something even stranger, this cosmic scout reminded us that the universe is full of surprises, and the next one might rewrite the rules entirely. Speaking of rewriting rules, let's turn to a world much closer to home. Just 4 light-years away, a planet orbits our nearest stellar neighbor, Proxima Centauri, in the so-called habitable zone. But could it really harbor life, or is it a radiation-blasted wasteland? The answers might surprise you. Shifting our gaze to our cosmic backyard, let's explore the tantalizing possibilities of Proxima Centauri b, the closest known exoplanet to Earth, just a stone's throw away in galactic terms. Orbiting Proxima Centauri, a red dwarf star a mere 4 light-years from us, this world sits snugly within its star's habitable zone, where temperatures could allow liquid water to exist. But here's the catch: habitable zone doesn't always mean habitable. Proxima b is a rocky planet, roughly 1.3 times Earth's mass, which immediately makes it intriguing. Its tight orbit, completing a year in just 11 Earth days, means it's likely tidally locked, with one side perpetually facing its star and the other shrouded in eternal night. At first glance, that sounds like a recipe for extremes, a scorching day side and a frozen night side. Yet, theoretical models suggest that if Proxima b has a substantial atmosphere, heat could circulate, tempering those extremes and creating pockets where life might cling on. But the real hurdle, Proxima Centauri itself. Red dwarfs are notorious for their violent tantrums. This star bombards its planets with frequent, powerful flares, bursts of radiation that could strip away atmospheres and sterilize surfaces. In fact, one observed flare from Proxima Centauri was so intense it briefly made the star 10,000 times brighter in ultraviolet light. For any potential life on Proxima b, that's like sitting next to a cosmic blowtorch. Yet, life on Earth has proven resilient in the harshest conditions, from deep sea vents to radioactive pools. Some scientists speculate that Proxima b's hypothetical organisms might huddle underground or underwater, shielded by ice or rock. Others propose that a thick atmosphere or a global ocean could diffuse the radiation's impact. There's even a wild card: magnetic fields. If Proxima b has one, it might deflect some of the worst stellar aggression, much like Earth's magnetic field protects us from solar winds. The real excitement lies in what we don't know yet. Upcoming telescopes, like the extremely large telescope in Chile, could analyze Proxima b's atmosphere, if it has one, for biosignatures like oxygen or methane. Detecting these gases would be a game-changer, hinting at processes we typically associate with life. And let's not forget Breakthrough Starshot, that audacious plan to send tiny, laser-propelled probes to the Proxima system within our lifetimes. While it's a long shot, the mere possibility of snapping close-up photos of another world's surface is enough to set imaginations racing. Proxima b forces us to rethink what habitable really means. It's a reminder that life, if it exists, might thrive in ways we haven't even imagined. And as the nearest exoplanet to Earth, it's also a symbol of hope, a place where, one day, we might find our first definitive answer to the question, are we alone? Now, let's venture to a moon where the chemistry of life might be writing itself in real time. Saturn's enigmatic Titan, with its methane lakes and organic haze, could be a laboratory for the very building blocks of life, just not as we know it. Turning our attention to a world that feels both alien and strangely familiar, Saturn's largest moon, Titan, presents a landscape straight out of science fiction, but with chemistry that might hold the keys to life's origins. Unlike any other moon in our solar system, Titan boasts a thick, hazy atmosphere and liquid lakes, though not of water. Instead, they're filled with methane and ethane, creating a bizarre yet mesmerizing environment where the rules of chemistry play out in ways that eerily resemble Earth's primordial past. The Cassini-Huygens mission, which explored Saturn and its moons between 2004 and 2017, revealed Titan as a hive of organic activity. Its atmosphere is rich with nitrogen and methane, and when sunlight interacts with these gases, it triggers a cascade of chemical reactions, producing complex molecules like hydrocarbons and nitriles. These compounds rain down onto Titan's surface, forming dunes of organic sand and filling its lakes with liquid methane. This process mirrors what scientists believe happened on Earth billions of years ago, when similar molecules accumulated in our planet's early oceans, setting the stage for life's emergence. But Titan's chemistry goes even further. Cassini detected vinyl cyanide in its atmosphere, a molecule that on Earth can form cell-like membranes in liquid methane. While life as we know it relies on water, Titan's frigid temperatures hovering around -180 degrees Celsius mean any potential life would have to be radically different, perhaps using methane as a solvent instead. This raises a tantalizing question. Could Titan's methane lakes host exotic hydrocarbon-based life forms? The upcoming Dragonfly mission, set to launch in 2027 and arrive in the mid-2030s, aims to find out. This nuclear-powered drone will hop across Titan's surface, sampling its organic-rich sediments and studying its atmosphere in unprecedented detail. Dragonfly's instruments will search for chemical signatures that could indicate prebiotic processes or even signs of life. One key target is Selk Crater, a site where water and organic materials may have mixed in the past, creating a potential hotspot for complex chemistry. What makes Titan so compelling is its duality. It's a frozen relic of the early solar system, yet also a dynamic world where chemistry is actively building the ingredients for life. If Dragonfly uncovers evidence that these processes have advanced toward biology, it would revolutionize our understanding of life's potential in the cosmos. Titan challenges us to broaden our definition of habitability, reminding us that life might not need water or sunlight, just the right mix of chemistry and time. As we continue our journey through the cosmos, let's zoom in on another enigmatic signal that has puzzled scientists for decades: the WOW signal, a burst of radio waves that still stands as one of the most compelling hints of extraterrestrial intelligence. Now, let's shift our gaze to one of the most electrifying mysteries in modern astronomy: fast radio bursts, or FRB. These are incredibly powerful bursts of radio waves that last just milliseconds, yet release as much energy as the sun does in days. First detected in 2007, FRBs have baffled scientists for years, but the plot thickened when we discovered some of them repeat. The most famous of these, FRB 121102, has been flashing sporadically since its discovery, sparking debates about whether we're witnessing natural cosmic fireworks or something far more extraordinary. What makes repeating FRBs so intriguing is their unpredictability. Unlike one-off bursts which could be explained by cataclysmic events like neutron star collisions, repeaters like FRB 121102 defy simple explanations. Some scientists have theorized that these precise, high-energy signals could be technological in origin, perhaps evidence of advanced alien civilizations. The idea isn't as far-fetched as it sounds. If humans were to transmit a signal across interstellar space, we'd likely use concentrated radio waves, much like FRBs. Proposals have even suggested they could be powering alien light sails or leaking from massive communication networks. But before we jump to extraterrestrial conclusions, nature offers compelling alternatives. Magnetar's highly magnetized neutron stars are leading suspects, These cosmic powerhouses can produce violent flares, and in 2020, astronomers finally linked an FRB to a magnetar in our own galaxy, adding weight to this theory. Another possibility is that FRBs are born from interactions between dense objects like black holes and their surroundings, or even from the collapse of exotic stellar remnants. The truth is, the universe is full of extreme phenomena we're only beginning to understand. Beyond their mystery, FRBs serve as invaluable cosmic tools. As these bursts travel across space, they pass through ionized gas and magnetic fields, leaving subtle imprints on their signals. By studying these distortions, astronomers can map the universe's otherwise invisible matter, piecing together the structure of the cosmos itself. It's like using a flashlight in a foggy room. The way the light scatters reveals what's hidden in the darkness. Whether FRBs are natural marvels or something more, they remind us how much we have yet to learn. Upcoming telescopes like the Square Kilometre Array will scan the skies with unprecedented sensitivity, potentially cracking the code of these enigmatic signals. Until then, FRBs remain one of astronomy's greatest puzzles, a whisper from the cosmos that could rewrite our understanding of the universe or even our place within it. And speaking of cosmic whispers, few have captured the imagination like the next discovery on our list, the infamous WOW signal, a fleeting radio burst that still stands as one of the most tantalizing hints of extraterrestrial contact ever recorded. Now let's turn our attention to a moment in history that still sends shivers down the spines of astronomers, the legendary WOW signal. Detected on August 15, 1977 by Ohio State University's Big Ear radio telescope, this 72-second burst of narrowband radio waves was so remarkable that astronomer Jerry Amon circled it on the printout and scribbled, "Wow." Next to it, giving the signal its iconic name. What made it stand out? It was 30 times stronger than the background noise, matched the expected frequency of hydrogen, a likely candidate for interstellar communication, and vanished as suddenly as it appeared, never to be heard again. For decades, the WOW signal has been the gold standard of potential extraterrestrial contact, a tantalizing one-off that refuses to be explained away. Early theories leaned heavily toward an intelligent origin, the signal's narrowband nature, like a laser-focused radio beacon, seemed almost engineered, and its frequency aligned perfectly with the water hole, a quiet band of the radio spectrum between hydrogen and hydroxyl wavelengths, where scientists hypothesized aliens might transmit to avoid cosmic interference. But despite countless follow-up searches, including projects by SETI, the signal never repeated, leaving us with more questions than answers. In recent years, skeptics have proposed earthly explanations. One leading theory suggests the signal might have been a reflection of radio emissions from a passing comet. In 2016, researcher Antonio Paris argued that comets 266P/Christensen and 335P/Gibbs, which were transiting the same patch of sky in 1977, could have been the culprits. Their hydrogen-rich clouds, illuminated by the sun, might have produced the brief, intense burst, but this idea has faced pushback. Critics point out that comets don't typically emit such strong, narrowband signals, and the Big Ear telescope's design made it unlikely to confuse a comet's diffuse glow with a pinpoint radio source. What keeps the WOW signal alive in our collective imagination isn't just the mystery, it's the cultural weight it carries. For SETI researchers, it's a reminder of how close we might have come to a groundbreaking discovery and how fragile such moments can be. The signal emerged from a time when SETI was still in its infancy, and its detection was almost accidental. Today, with advanced tools like the Allen Telescope Array and Breakthrough Listen scanning the skies, we're better equipped to catch and verify potential signals. But the WOW signal remains a humbling lesson in patience and perspective. The signal also taps into something deeper, our longing for connection. In a universe that's overwhelmingly silent, that single wow is a flare in the darkness, a whisper that says someone might be out there. Whether it was a comet, a glitch, or something far more profound, its legacy endures. And as we continue to listen, the wow signal stands as both a milestone and a motivator, proof that the cosmos still holds surprises and that the next great discovery could be just one radio burst away. Speaking of cosmic enigmas, our journey now takes us to another fascinating idea: the possibility that life itself might be a hitchhiker, traveling between stars on asteroids and comets. This theory, known as panspermia, suggests that the building blocks of life, or even living organisms, could be scattered across the galaxy, just waiting for the right conditions to take root. Now, let's dive into a theory that blurs the line between science and science fiction: the idea that life might not have originated on Earth at all. Instead, it could have arrived here from the depths of space, hitching a ride on asteroids or comets. This concept, known as panspermia, suggests that the building blocks of life, or even living organisms themselves, are scattered throughout the cosmos, just waiting for the right conditions to take hold. One of the most compelling pieces of evidence for panspermia comes from the bizarre interstellar visitors that have zipped through our solar system in recent years. Take Oumuamua, the first known interstellar object detected in 2017. Its elongated shape, unusual acceleration, and lack of a visible comet tail left scientists scratching their heads. While some speculated it might be an alien probe, others proposed it could be a fragment of a Pluto-like world, rich in organic molecules. Then there's Comet Borisov, another interstellar traveler discovered in 2019, which carried water and gas similar to comets in our own solar system. These objects tell us something profound. The universe is constantly exchanging material, and some of it might carry the ingredients for life. But how could life survive such a journey? Experiments here on Earth suggest it's not as far-fetched as it sounds. Tardigrades, those tiny, indestructible water bears, have been shown to endure the vacuum of space, extreme radiation, and even the crushing pressures of re-entry. In 2007, scientists exposed these hardy microbes to outer space for 10 days aboard the European Space Agency's Phosphine M3 mission, and they not only survived but later reproduced. Even more astonishing, certain bacteria and lichens have thrived under similar conditions, tucked away in protective nooks on spacecraft or embedded in simulated meteorites. These findings hint that microbial life could, in theory, endure the long, harsh trek between stars. Panspermia isn't just about microbes catching a ride on space rocks. Some scientists argue that complex organic molecules, like amino acids, could also be delivered to young planets this way. We've already found these compounds in meteorites like the Murchison meteorite, which landed in Australia in 1969 and contained over 90 different amino acids. If such molecules are common in space, they could act as cosmic seeds, jump-starting life wherever conditions allow. Critics, of course, raise valid questions. Could fragile organic material really survive the violent impacts and intense radiation of interstellar travel? And even if it did, how likely is it to find a habitable new home? Yet panspermia offers a tantalizing solution to one of astrobiology's biggest puzzles. If life arose so quickly on early Earth, could it have had a head start from elsewhere? The theory also reshapes how we think about life's distribution in the universe. Instead of emerging independently on isolated planets, life might be a shared cosmic phenomenon, spreading like interstellar dandelion seeds. Future missions like Japan's Hayabusa 2 and NASA OSIRIS-REx could provide more clues by analyzing samples from asteroids rich in organic material. As we continue to explore, panspermia reminds us that Earth might not be a solitary cradle of life but part of a vast, interconnected web. And if that's true, the next time we find signs of life beyond our planet, we might just be meeting distant cousins, fellow travelers on this grand cosmic journey. Turning our gaze to another frontier, consider the regions of our galaxy where life might find its most welcoming home, a concept known as the Galactic Habitable Zone. Now, let's zoom out from individual planets and moons to consider the broader canvas of our galaxy, because not all regions of the Milky Way are equally welcoming to life. Imagine the galaxy as a vast metropolis with bustling downtown areas, quiet suburbs, and everything in between. Just as some neighborhoods are safer or more resource-rich than others, certain parts of the galaxy offer the perfect conditions for life to thrive. This idea is known as the Galactic Habitable Zone, a sweet spot where the cosmic environment is just right for nurturing living worlds. The Galactic Habitable Zone is like a life-friendly ring encircling the Milky Way, lying roughly between 25,000 and 40,000 light-years from the galactic center. Here, stars are far enough from the chaos of the inner galaxy, where deadly supernova and gamma-ray bursts are more common, yet close enough to benefit from a steady supply of heavy elements like iron, carbon, and oxygen. These elements, forged in the hearts of ancient stars and scattered by their explosive deaths, are the building blocks of planets and life itself. Without them, Earth-like worlds couldn't form. Compare this to the galactic center, a region that's anything but hospitable. Near the supermassive black hole Sagittarius, a star, stars are packed so tightly that gravitational tugs could fling planets from their orbits. Radiation from countless stellar explosions bathes the area, stripping away atmospheres and sterilizing surfaces. It's a cosmic dead zone where life as we know it would struggle to take hold. On the other hand, the galaxy's outer edges are too quiet. Stars there are metal poor, meaning they lack the heavy elements needed to form rocky planets. Without these materials, the chances of life emerging drop dramatically. Earth, as it turns out, sits in the Goldilocks region of the Galactic Habitable Zone. Our solar system orbits about 27,000 light-years from the center, in a relatively calm spiral arm where stellar densities are low enough to minimize catastrophic events, but high enough to ensure a rich supply of planet-forming materials. This prime location has shielded us from the worst of the galaxy's violence while providing the resources necessary for life to flourish. But the Galactic Habitable Zone isn't static. Over billions of years, as the Milky Way evolves, this life-friendly region may shift. Stars migrate and the distribution of metals changes. Some scientists even suggest that early in the galaxy's history, the habitable zone was narrower, making life rarer in the distant past. As we search for other Earth-like worlds, this concept reminds us to focus on stars that share our galactic neighborhood, those orbiting in similar, life-friendly regions. This idea also raises a fascinating question. If life is more likely in certain parts of the galaxy, could we be surrounded by cosmic neighbors just waiting to be discovered? Future telescopes like the James Webb Space Telescope will help us peer into these promising zones, hunting for biosignatures on distant exoplanets. Until then, the Galactic Habitable Zone gives us a roadmap, a way to narrow our search for life in the vastness of space. Speaking of narrowing the search, let's turn our attention to a world that's defying expectations. A super-Earth called LHS 1140b, where the conditions might be just right for an ocean of water or even magma. Now, let's take a closer look at a world that might just blur the line between science fiction and reality. LHS 1140b. This intriguing exoplanet, orbiting a small, dim red dwarf star about 40 light-years away, has captured the attention of astronomers for one compelling reason. It's one of the most promising super-Earths we've found in the hunt for habitable worlds. What makes LHS 1140b stand out is its extraordinary density. Measurements suggest it's roughly 1.7 times the size of Earth but packs nearly 7 times the mass. That incredible heft points to a rocky composition, possibly with a dense iron core like our own planet. But here's where things get even more fascinating. Some models indicate that this super-Earth could harbor a vast magma ocean beneath its surface, or even a thick layer of water. Imagine a global sea deeper than anything on Earth. If true, this could create the perfect conditions for hydrothermal vents, those life-nurturing hotspots we've seen in Earth's deepest oceans, the planet's location adds to its allure. It sits snugly within its star's habitable zone, where temperatures might allow liquid water to exist. But LHS 1140b's star is a red dwarf which comes with its own challenges. These stars are notorious for their violent flares, which can strip atmospheres away over time. Yet, recent studies hint that this planet might have held onto a substantial atmosphere, thanks to its strong gravity and possible magnetic field. That's a game changer because an atmosphere could mean protection from radiation and even the right chemistry for life. This is where the James Webb Space Telescope enters the picture. With its unparalleled ability to analyze starlight filtering through exoplanet atmospheres, Webb could soon reveal whether LHS 1140b has gases like oxygen, methane, or carbon dioxide potential biosignatures that might hint at biological activity. Imagine the implications if we detect oxygen here. On Earth, oxygen is largely produced by life, so finding it on another world would be a seismic discovery. But let's temper excitement with caution. Oxygen can also arise from non-biological processes, like the breakdown of water by ultraviolet light. That's why astronomers won't jump to conclusions. Instead, they'll look for combinations of gases like oxygen alongside methane that are hard to explain without life. It's this meticulous detective work that makes LHS 1140b such a compelling target. Every observation brings us closer to answering whether we're alone in the cosmos. As we wait for Webb's findings, one thing is clear. LHS 1140b is a reminder that habitable worlds might come in unexpected forms. Whether it's a water world, a magma-covered giant, or something entirely different, this super-Earth is rewriting the rules of where and how life could exist. And with each new discovery, the universe feels a little less lonely. Now, let's shift gears to a question that has puzzled scientists for decades. If the universe is so vast and ancient, why haven't we found any clear signs of extraterrestrial civilizations? This brings us to one of the most enduring mysteries in astronomy, the Fermi paradox. Now, let's tackle one of the most haunting questions in astronomy. If the universe is so unimaginably vast with billions of potentially habitable planets, why does it feel so empty? This is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" On the surface, the numbers seem to favor life. Our galaxy alone contains hundreds of billions of stars, many with planets in habitable zones. Even if only a tiny fraction of those worlds developed civilizations, the Milky Way should be teeming with activity. Yet, despite decades of searching, we've found no definitive signs of alien intelligence, no radio signals, no megastructures, no interstellar probes. This eerie silence forces us to reconsider old assumptions and explore bold new explanations. One provocative idea is the zoo hypothesis. Imagine advanced civilizations observing us from a distance, much like we study animals in a nature reserve. They might avoid contact to let humanity develop naturally or to prevent cultural contamination. While this sounds like science fiction, it's a serious proposal among scientists grappling with the paradox. The challenge, of course, is proving it. If aliens are deliberately hiding, our current methods of detection might never find them. Then there's the possibility we're looking for the wrong clues. Traditional SETI searches focus on radio signals, but what if advanced societies communicate using neutrino beams, quantum entanglement, or other technologies we can't yet comprehend? Or consider technosignatures evidence of alien engineering, like Dyson swarms harvesting starlight or industrial pollutants in exoplanet atmospheres. The James Webb Space Telescope could revolutionize this search by spotting such anomalies in distant worlds. But not all solutions are optimistic. The Great Filter theory suggests that some catastrophic obstacle, nuclear war, runaway AI, or environmental collapse prevents civilizations from surviving long enough to colonize the galaxy. If true, humanity's fate might hinge on whether we've already passed this filter or if it still lies ahead. On the flip side, we might simply be early. The universe is 13.8 billion years old, but complex life could be a recent phenomenon. If intelligent species are rare or slow to emerge, we might be among the first to ask these questions. The Fermi paradox isn't just a thought experiment, it's a mirror reflecting our own existential uncertainties. With tools like JWST sharpening our cosmic vision, we're closer than ever to uncovering answers. Whether the truth involves hidden watchers, tragic filters, or something beyond our imagination, one thing is certain: the silence of the cosmos is a puzzle begging to be solved. Now, let's turn our attention to another cosmic enigma that once sparked wild speculation about alien megastructures: the bizarre flickering of KSE 8462852, better known as Tabby's star. Now, shifting our gaze to one of the most perplexing stars in the cosmos, let's unravel the mystery of KSE 8462852, nicknamed Tabby's star after astronomer Tabitha Boyajian, who first brought its strange behavior to light. Nestled in the constellation Cygnus, this star captured global attention when data from the Kepler Space Telescope revealed its unprecedented and erratic dimming patterns. Unlike typical exoplanet transits, which cause predictable periodic dips in starlight, Tabby's star dimmed by staggering amounts, up to 22% at times in irregular, jagged intervals. This wasn't just unusual, it defied every conventional explanation astronomers had at the time. The strangeness sparked a flood of theories, but one electrified the public imagination: the idea that this could be evidence of an alien megastructure, specifically a Dyson sphere. Proposed by physicist Freeman Dyson in the 1960s, a Dyson sphere is a hypothetical shell of solar panels or habitats built by an advanced civilization to harness a star's energy. If such a structure were partially completed or arranged in a swarm around Tabby's star, it could in theory block light in the erratic ways observed. For a brief moment, science fiction seemed to brush against reality, but science thrives on scrutiny, and follow-up studies began chipping away at the extraterrestrial hypothesis. Observations from the Hubble Space Telescope and the Los Cumbres Observatory revealed that the dimming affected different wavelengths of light unevenly, a telltale sign of something mundane: dust. Fine cosmic dust likely from a swarm of comets, a shattered planet, or interstellar debris could scatter and absorb starlight in chaotic ways. By 2018, the consensus tilted firmly toward natural explanations, with dust clouds emerging as the prime suspect. Yet the story doesn't end there. Tabby's star still holds onto its share of secrets. For one, the sheer amount of dust required to explain the dimming is staggering, far beyond anything seen in our own solar system. Some researchers suggest the star might be recovering from a recent cataclysmic event, like a planetary collision that ejected vast amounts of material into its orbit. Others point to the star's own peculiarities: it's slightly hotter and more massive than the Sun, as potential factors in its bizarre behavior. What makes Tabby's star so compelling isn't just the fading hope of aliens, but the reminder that the universe is full of phenomena we've yet to fully understand. It's a cosmic detective story where each clue leads to new questions. And while the dust theory may dominate today, the door isn't entirely closed on more exotic possibilities. Future telescopes like the James Webb or the upcoming Vera C. Rubin Observatory could deliver the data needed to solve this puzzle once and for all. As we continue our journey through these cosmic discoveries, let's turn next to a finding that reshapes where we look for life's ingredients: the detection of organic molecules in the swirling disks of infant star systems. Moving from the mysteries of Tabby's star to the very building blocks of life itself, let's explore a discovery that suggests life's ingredients might be sprinkled across the cosmos. Using the Atacama Large Millimeter Array, or ALMA, astronomers have detected complex organic molecules swirling within the protoplanetary disks of young star systems, essentially the nurseries where planets are born. These findings aren't just exciting, they're revolutionary, hinting that the chemical foundations for life might be universal. Oumuamua sharp vision allowed scientists to identify molecules like methyl cyanide and even simple sugars orbiting infant stars hundreds of light years away. These aren't just random compounds, they're the same types of molecules that, on Earth, played a crucial role in the emergence of life. Methyl cyanide, for instance, is linked to the formation of amino acids, the very building blocks of proteins. To find such complexity in the chaotic environment of a young star system suggests that the universe might be preloaded with life's ingredients, waiting for the right conditions to spark something extraordinary. What makes this discovery so profound is the implication that Earth's chemistry might not be special. For decades, scientists wondered whether our planet's mix of organic molecules was a rare cosmic accident. But Oumuamua observations paint a different picture. These compounds appear to form naturally in the turbulent disks of gas and dust where planets take shape. In one notable case, the star system TW Hydrothermal, just under 200 light-years away, hosted a veritable soup of organic molecules, including formaldehyde and methanol. These are the kinds of materials that, given enough time and the right environment, could theoretically evolve into more complex structures, much like they did here on Earth. The parallels don't end there. Researchers have even spotted water vapor in these disks, along with other life-friendly molecules like carbon monoxide and hydrogen cyanide. Together, they form a sort of cosmic recipe book, with each ingredient playing a role in the chemistry that could eventually lead to life. It's as if the universe has a habit of mixing these materials wherever new planets are forming, raising the tantalizing possibility that the story of Earth's life might be repeating itself elsewhere. But how do these molecules survive the violent environment of a young star system? Protoplanetary disks are far from serene. They're churned by turbulence, radiation, and collisions. Yet somehow these fragile organic compounds endure. One theory suggests they form on icy grains of dust, shielded from harsh radiation, before getting incorporated into asteroids, comets, or even budding planets. This could mirror how Earth likely received its own organic inventory, delivered by bombardments of comets and meteorites billions of years ago. The presence of such molecules doesn't guarantee life, of course. It's like finding flour, eggs, and sugar in your kitchen. You have the ingredients, but you still need the right conditions to bake a cake. Still, Oumuamua discoveries dramatically widen the scope of where we might search for life beyond Earth. If these building blocks are common, then planets with the potential for life might be common too. Future telescopes, like the James Webb Space Telescope, could take the next step by probing the atmospheres of exoplanets for signs of these molecules in more mature systems. As we ponder the implications of these cosmic kitchens, our next discovery takes us even closer to the idea that life might exist in the most unexpected places, including a scorching, diamond-rich world known as 55 Cancri E. Shifting our gaze from the organic-rich nurseries of young stars to a world that defies expectations, let's turn our attention to 55 Cancri E, a planet so extreme it's earned the nickname the Hell Planet. Orbiting dangerously close to its sun-like star, this super-Earth is a blistering nightmare of molten surfaces and searing temperatures. Yet it might hold one of the most surprising secrets in the search for life, a thick, carbon-rich atmosphere. If life can exist here, it would force us to rewrite every rule we thought we knew about habitable worlds. 55 Cancri E is a world of contradictions. Roughly twice Earth's size and 8 times its mass, this planet completes an orbit in just 18 hours, with daytime temperatures hot enough to vaporize most metals. Some estimates suggest over 4,000 degrees Fahrenheit. For years, scientists assumed such a place would be a barren, airless rock. its atmosphere long since scorched away by relentless stellar radiation. But recent observations from the James Webb Space Telescope hint at something astonishing: a volatile atmosphere, possibly rich in carbon dioxide or even methane. If confirmed, this would mark the first time an atmosphere has been detected around a rocky planet orbiting a sun-like star, and it raises a tantalizing question: how could any atmosphere survive here? One theory suggests the planet's interior might be outgassing, releasing gases like carbon monoxide or hydrogen sulfide through volcanic vents. Another possibility is that its atmosphere is being constantly replenished by vaporized surface material, given that 55 Cancri E is so hot that parts of its crust may literally be evaporating. But the most intriguing speculation is that this atmosphere could be carbon-based, draped over a planet composed largely of diamonds. Yes, diamonds. Under extreme heat and pressure, carbon can crystallize, and some models suggest this world's interior might be a glittering, diamond-rich core. Imagine a planet where it rains molten diamonds, a scenario so bizarre it sounds like science fiction, yet it's grounded in real astrophysics. Now, let's push the boundaries even further. Could life exist in such a place? On Earth, we've discovered extremophiles microbes thriving in boiling hydrothermal vents, acidic lakes, or even the radioactive wreckage of nuclear reactors. If life can cling to existence in those environments, who's to say it couldn't adapt to the crushing heat and pressure of 55 Cancri E? Hypothetical organisms might harness chemical energy from volcanic gases or even the planet's carbon-rich chemistry, much like Earth's deep-sea bacteria survive on sulfur. Some astrobiologists speculate that life in such a world could exist in a vaporized form, floating in the upper atmosphere where temperatures are marginally less lethal. But here's the catch: even if life were possible, detecting it would be a monumental challenge. The planet's extreme conditions make traditional biosignatures like oxygen or methane unreliable. They could just as easily be produced by geological processes. Instead, scientists might need to look for more exotic clues, like unusual ratios of gases that hint at biological activity. This is where the James Webb Space Telescope could be a game changer, analyzing the planet's atmosphere in unprecedented detail. What makes 55 Cancri E so compelling isn't just the slim chance of life, it's the way it forces us to expand our imagination. If a planet this hostile can cling to an atmosphere, what does that say about the resilience of worlds elsewhere? And if life could exist here, where else might it be hiding? As we continue our cosmic journey, we'll next explore an even older mystery, one that takes us back to Earth's earliest days, and the fossils that might hold the key to life's universal origins. With our imagination stretched by the extremes of 55 Cancri E, let's now turn to a discovery much closer to home, one that could rewrite the very timeline of life itself. Hidden in the ancient rocks of Western Australia lies evidence of what might be the oldest life forms ever found on Earth, microfossils dating back an astonishing 3.5 billion years. These microscopic structures, discovered in the Pilbara region, resemble the shapes of modern bacteria, preserved in silica-rich deposits that once formed the floor of a primordial ocean. If confirmed as biological in origin, they wouldn't just be a window into Earth's distant past, they'd be a blueprint for what to search for on Mars, where conditions in its early history eerily mirrored our own planet's infancy. The Pilbara fossils, often called the apex chert microfossils, are tiny, some no larger than a human hair's width, but their implications are colossal. Found trapped in rocks that formed around hydrothermal vents, they appear to cluster in filaments and spheres, similar to colonies of modern microbes that thrive in extreme environments. The real debate, though, centers on whether these shapes were truly crafted by biology or are simply the result of geological processes mimicking life. Skeptics point out that heat and pressure over billions of years can distort minerals into lifelike patterns without any organic activity. Even the chemical signatures claimed as evidence of ancient metabolism, like certain carbon isotopes, can sometimes form without life's involvement. This controversy mirrors the challenges facing Mars exploration. The red planet's early history overlaps with Earth's in a critical way. Both had liquid water, thick atmospheres, and active geology around the same time. If life arose here in those conditions, why not there? NASA Perseverance rover is currently scouring Jezero Crater, a dried-up river delta, for rocks that might contain fossils akin to Pilbaras. But verifying them would require overcoming the same hurdles distinguishing between biology and geology in ancient, altered samples. One breakthrough came in 2019, when scientists analyzing the Pilbara fossils identified organic nitrogen compounds trapped inside them, a potential smoking gun for ancient life. Similarly, instruments like Perseverance's Sherlock spectrometer are designed to detect complex organic molecules in Martian rocks. But the gold standard would be bringing samples back to Earth, where labs could analyze them with tools far more precise than any rovers. That's why NASA's Mars Sample Return mission, slated for the 2030s, is so pivotal. What makes these ancient whispers of life so compelling isn't just their age, it's the way they force us to refine our definitions of proof. On Earth, skepticism has pushed researchers to develop ever more rigorous tests for biosignatures. The same scrutiny will apply to any claims of Martian life. But if the Pilbara fossils hold up, they suggest life took root astonishingly early in Earth's history, perhaps within a few 100 million years of the planet's formation. That speed implies life might not be a rare fluke, but a natural outcome wherever the right conditions persist. As we continue our cosmic detective work, this interplay between Earth and Mars raises a profound question. If life left traces here in the harshest extremes of deep time, what might still lie buried in the rust-colored sands of our neighboring world? Next, we'll confront one of the most unsettling answers to Fermi's famous paradox, a theory that suggests the universe might be hiding its inhabitants for a reason. Now, shifting our gaze from the ancient whispers of life on Earth to the vast, silent cosmos, let's explore one of the most unsettling theories about why the universe seems so quiet. Imagine a dark forest, not the kind filled with trees, but one teeming with hidden civilizations, each too afraid to make a sound. This is the heart of the dark forest hypothesis, a chilling answer to the Fermi paradox, which asks, where is everybody? If the universe is so vast and old, why haven't we found any traces of intelligent life? The dark forest hypothesis suggests a grim possibility. Advanced civilizations might be hiding on purpose, staying silent to avoid annihilation. The idea comes from game theory, the same field that studies strategic decision-making in economics and politics. Picture two hunters in a dark forest, each unaware of the other's intentions. If one reveals their location, the other might shoot first out of fear or self-preservation. In this scenario, silence is the safest strategy. Applied to the cosmos, it means any civilization that broadcasts its existence risks attracting the attention of a more advanced and potentially hostile neighbor. This theory gained traction thanks to science fiction, particularly Liu Cixin's The Three-Body Problem series. But it's not just fiction. Some scientists take it seriously because it aligns with certain logical assumptions. First, resources in the universe are finite. Planets, energy, and materials are limited, which could drive competition. Second, technological progress isn't uniform. One civilization might leap centuries ahead of another, creating a power imbalance. And third, communication delays across light years make trust impossible. By the time a friendly signal arrives, the sender's intentions could have changed. But why would civilizations assume the worst? History offers a sobering lesson. On Earth, when cultures with uneven technology have met, the results were often catastrophic for the less advanced group. If this pattern holds universally, it's rational for civilizations to stay hidden. even our own efforts, like the Arecibo message or the Golden Records on Voyager, might be seen as reckless by proponents of this theory. Not everyone agrees, of course. Critics argue the dark forest hypothesis is overly pessimistic, ignoring cooperative possibilities or the likelihood that advanced civilizations would outgrow violent competition. Others point out that hiding forever is impractical. Energy use or cosmic events would eventually reveal a civilization's presence. Still, the hypothesis forces us to confront uncomfortable questions about our place in the universe. As we listen for alien signals or send out our own, the dark forest reminds us that the cosmos might not be a friendly neighborhood. It's a place where silence could be survival, and the first to speak might be the first to fall. Next, we'll turn to a discovery that proves life, at least in some forms, is far tougher than we ever imagined: tiny creatures surviving the vacuum of space itself. But what if life doesn't need advanced civilizations or hidden intentions to thrive in the cosmos? Sometimes survival comes down to sheer resilience, and few creatures prove that better than the unassuming tardigrade. These microscopic animals, affectionately nicknamed water bears, might just be the toughest organisms we've ever discovered. Let's dive into the extraordinary experiments that have shown tardigrades surviving conditions that would obliterate most other life forms, and what this means for our search for life beyond Earth. In 2007, scientists sent a group of tardigrades into low Earth orbit aboard a European Space Agency mission, exposing them to the vacuum of space, intense radiation, and freezing temperatures. The results were staggering. Not only did many survive, but some even reproduced after returning to Earth. Imagine enduring the void of space without protection, no oxygen, no pressure, just cosmic rays blasting through your tiny body and still bouncing back as if nothing happened. Tardigrades owe this superpower to a process called cryptobiosis, where they essentially shut down their metabolism and curl into a dehydrated ball known as a ton. In this state, they can withstand temperatures ranging from near absolute zero to over 300 degrees Fahrenheit, pressures 6 times greater than the deepest ocean trenches, and radiation doses hundreds of times higher than what would kill a human. Some studies suggest they could even survive the aftermath of an asteroid impact or a nearby supernova. This raises fascinating questions about panspermia, the idea that life could hitchhike across the cosmos on asteroids or comets. If tardigrades can survive space, could other microorganisms do the same? We've already found organic molecules on meteorites, and with interstellar objects like Oumuamua passing through our solar system, the possibility isn't as far-fetched as it sounds. Life might not need to originate on every habitable planet. It could simply spread like seeds on the wind. Beyond panspermia, tardigrades offer hope for terraforming harsh worlds. If we ever aim to colonize Mars or Europa, organisms like these could help us engineer more hospitable environments. Scientists are already studying their unique proteins, which protect their DNA from radiation damage, to develop better shielding for astronauts or even radiation-resistant crops. So, while the dark forest hypothesis paints a cautious picture of the cosmos, tardigrades remind us that life, in its simplest forms, is tenacious. Whether clinging to a comet or enduring the void, these tiny survivors hint that the universe might be far more inhabited than we think, just not in the ways we expected. Next, we'll revisit one of the most baffling cosmic mysteries, the strange flickering of a star once thought to harbor an alien megastructure. Shifting our gaze to another cosmic puzzle, let's return to Boyajian star, officially known as KSE 8462852. This distant sun, located over 1,000 light-years away in the constellation Cygnus, first captured global attention in 2015 when astronomers noticed its bizarre, unpredictable dimming, sometimes by as much as 22%. No ordinary star behaves like this, and for a while, even the wildest theories struggled to explain it. Some suggested an alien megastructure like a Dyson swarm might be blocking its light. But science thrives on curiosity and skepticism, and new observations have reshaped the story. Initial excitement around Boyajian's star centered on its erratic flickers, which defied natural explanations. Planets, even large ones, typically cause uniform, periodic dips in starlight, but this star's dimming was irregular, deep, and lasted for days or weeks. When astronomer Tabitha Boyajian and her team, aided by citizen scientists from the Planet Hunters project, ruled out instrumental errors or nearby asteroids, the mystery deepened. The internet exploded with speculation, including the tantalizing idea that an advanced civilization had constructed a massive energy harvesting array around the star. However, science marches on, and follow-up studies have peeled back layers of the enigma. Observations from ground-based telescopes and space instruments like the Hubble Space Telescope revealed that the dimming patterns weren't consistent with solid megastructures. Instead, they pointed to uneven clouds of dust, likely from cometary fragments or planetary debris, passing in front of the star. In 2018, detailed spectroscopy confirmed this. The starlight dimmed more at blue wavelengths than red, a telltale sign of fine dust particles scattering light. Yet the story isn't entirely closed. Some anomalies remain. The dust clouds would need to be enormous, far larger than anything in our solar system, and their origins are still unclear. Could a recent planetary collision or a swarm of icy bodies explain it? Or is there another, undiscovered phenomenon at play? The key takeaway here isn't just about debunking alien megastructures. It's a testament to how citizen science, collective curiosity, and rigorous follow-up can transform a headline-grabbing mystery into a nuanced cosmic lesson. What's equally remarkable is how this star became a cultural touchstone. It bridged the gap between professional astronomers and amateur stargazers, proving that everyone can contribute to cutting-edge science. Projects like Planet Hunters, where volunteers sift through telescope data, have since identified other unusual stars, showcasing the power of collaborative discovery. As we continue to monitor Boyajian's star, it reminds us that the universe loves a good puzzle. Whether the answer lies in exotic dust or something even stranger, the journey to uncover it has already reshaped how we search for cosmic anomalies. Up next, we'll explore another frontier in the hunt for extraterrestrial life, the hidden potential of moons orbiting distant gas giants, where tides and chemistry might forge unexpected havens for life. Turning our attention to the unseen worlds lurking in the shadows of gas giants, let's dive into the tantalizing possibility of exomoons, hidden oases that could defy our expectations of habitability. Picture Pandora from Avatar, but real, a moon bathed in the glow of a nearby planet where tides and chemistry might conspire to create environments ripe for life. For decades, our search for life beyond Earth fixated on planets, but moons orbiting gas giants like Jupiter's Europa or Saturn's Enceladus have taught us that smaller worlds can harbor vast oceans and even geothermal energy. The same could be true in other star systems. In 2018, astronomers using data from the Kepler Space Telescope announced the first compelling candidate for an exomoon, dubbed Kepler 1625b moon. This potential moon, roughly the size of Neptune, orbits a Jupiter-like planet in the habitable zone of its star. While its sheer size makes it unlikely to host life as we know it, the discovery cracked open the door to a new frontier. Exomoons as small as Earth with the right conditions for liquid water and organic chemistry. What makes these moons so intriguing? Tidal heating. Just as Jupiter's gravity stretches and squeezes Io, fueling its violent volcanoes, a gas giant's pull could keep a moon's subsurface ocean liquid, even far from a star's warmth. Models suggest that exomoons with elliptical orbits would experience intense tidal friction, generating enough heat to maintain oceans beneath icy shells. Some simulations even propose that such moons could develop atmospheres from volcanic outgassing, creating layered environments where life might emerge. But detecting these moons is no easy feat. Their faint signals are drowned out by the glare of their host planets. Future telescopes like the James Webb Space Telescope or the upcoming European Extremely Large Telescope might spot chemical signatures like oxygen or methane in an exomoon's atmosphere. Others propose hunting for gravitational wobbles in a planet's transit timing, a subtle clue that a moon is tugging on its giant neighbor. The implications are staggering. If life thrives on exomoons, the galaxy's habitable real estate could explode. Gas giants are common, and many orbit in their star's habitable zones. Each could host multiple moons, each with its own story. Imagine a system where one moon is a frozen wasteland, while another, just next door, simmers with tidal warmth and chemistry ripe for life. While we haven't confirmed an Earth-sized exomoon yet, the hunt is accelerating. And if we find one, it could rewrite the rules of astrobiology. Up next, we'll examine another cosmic whisper, a mysterious radio signal that briefly had scientists questioning whether we'd finally heard from another civilization. Shifting our gaze from hidden moons to distant stars, let's revisit a moment in 2015 that sent ripples through the astronomy community. A mysterious radio signal from a Sun-like star named HD 164595. Detected by Russia's Ratan 600 radio telescope, this burst of energy appeared to originate from a star just 94 light-years away, a stone's throw in cosmic terms. For a brief, electrifying moment, it seemed humanity might have stumbled upon a deliberate transmission from another civilization. The signal stood out for two reasons. First, its frequency around 11 GHz was eerily close to what scientists predict an advanced civilization might use for interstellar communication. Second, its intensity suggested a source far more powerful than any natural cosmic phenomenon. The excitement was palpable. Could this finally be the long-awaited hello from the stars? SETI researchers swiftly trained their telescopes on HD 164595, hoping to catch a repeat, but the signal never reappeared. As the initial buzz faded, skepticism took hold. Closer analysis revealed a more mundane truth. The signal was likely terrestrial interference, possibly from a passing satellite or military radar. While disappointing, this episode became a masterclass in how SETI separates hope from evidence. Every year, telescopes detect countless cosmic signals, but the vast majority are natural pulsars, quasars, or human-made noise. To weed out false alarms, SETI applies strict criteria. A genuine alien signal would need to be narrowband, focused on one frequency, persistent, and originate from a fixed point in space, ruling out satellites or atmospheric effects. The HD 164595 incident underscores a critical lesson in astrobiology. Extraordinary claims demand extraordinary evidence. It's easy to let imagination fill the gaps, especially when the stakes are as high as confirming we're not alone. But science thrives on rigor. Even the infamous WOW signal of 1977, still unexplained after decades, lacks the repeatability needed to claim a definitive extraterrestrial origin. This isn't to dismiss the search. False alarms like HD 164595 refine our methods, teaching us to listen more carefully. Future telescopes like the Square Kilometre Array will scan millions of stars with unprecedented sensitivity, filtering out interference in real time. Until then, each ambiguous signal, whether a cosmic whisper or a satellite's blip, sharpens our tools and temperance, because in the end, the greatest discovery won't be a single signal, but the patience and precision to recognize it when it truly arrives. Now, let's turn to another cosmic enigma, this time closer to home. Recent findings from the Parker Solar Probe suggest Venus, long written off as a hellscape, might still hold secrets in its swirling clouds. But just as we were ready to dismiss Venus as a lifeless inferno, the Parker Solar Probe swooped in with a plot twist no one saw coming. During a routine gravity assist flyby in 2020, this sun-studying spacecraft detected something bizarre in Venus's upper atmosphere, chemical signatures eerily similar to those produced by certain Earth microbes. Suddenly, the possibility of life floating in Venus's sulfuric acid clouds was back on the table. Here's what makes this finding extraordinary. 50 kilometers above Venus's scorching surface, temperatures and pressures resemble Earth's tropics, a stark contrast to the crushing, lead-melting conditions below. The probe's instruments picked up traces of phosphine and other complex molecules that, on our planet, are almost exclusively tied to biological activity. While volcanic eruptions or exotic chemistry could theoretically produce these compounds, scientists still haven't found a convincing non-biological explanation for the concentrations observed. This discovery threw gasoline on the smoldering phosphine debate from 2020. Back then, astronomers had controversially reported phosphine in Venus's clouds, a claim later challenged as possible data artifacts. But Parker's independent detection using entirely different instruments lent fresh credibility to the idea. It's as if two separate detectives stumbled upon the same cryptic clue. The implications are staggering. If microbes exist in Venus's atmosphere, they'd likely be extremophiles unlike anything on Earth, thriving in droplets of sulfuric acid. Some scientists speculate they could resemble high-altitude microbes in our own skies, perhaps even employing a bizarre form of photosynthesis using sulfur instead of carbon dioxide. Others caution that extraordinary claims require extraordinary proof. After all, Venus's atmosphere is a chemical labyrinth we're only beginning to decode. The good news, help is on the way. In the next decade, 3 bold missions aim to crack this mystery. NASA Da Vinci probe will plunge through Venus's atmosphere in 2029, sniffing for phosphine and organic molecules all the way down. Meanwhile, Veritas will map surface volcanism that could seed the clouds with chemicals, and Europe's Envision orbiter will analyze cloud composition in unprecedented detail. Even private efforts like Rocket Lab plan to send a life-hunting probe by 2023. What makes this chapter so thrilling is its unpredictability. Venus was supposed to be a cautionary tale of runaway greenhouse effects, not a contender for harboring life. Yet nature keeps reminding us life finds a way in the most unexpected places. Whether the final answer is yes or no, these missions will rewrite our understanding of habitable zones. Because if life can persist in the acidic skies of Venus, what other cosmic surprises might be waiting? Now, let's journey from the shrouded mysteries of Venus to a celestial phenomenon that baffled astronomers for years, the strange flickers of a star 700 light-years away, where some dared to imagine alien megastructures at work. Shifting our gaze from Venus to the depths of space, we encounter an entirely different cosmic puzzle, one that pulses with mystery. The Crab Nebula, a sprawling remnant of a supernova witnessed on Earth in the year 1054, has long been a textbook example of stellar death. But recent observations have revealed something unexpected, strange, erratic bursts of energy that defy conventional explanations. For a brief moment, these anomalies even sparked wild speculation about extraterrestrial intelligence tampering with cosmic machinery. At the heart of this enigma lies the Crab Pulsar, a rapidly spinning neutron star left behind by the supernova. Like a lighthouse, it emits regular beams of radiation which astronomers have monitored for decades. Yet in 2021, telescopes detected sudden, intense spikes in gamma rays and X-rays, some flaring up 30 times brighter than the pulsar's normal output. These weren't minor fluctuations, they were violent, unpredictable surges lasting mere milliseconds. The sheer energy involved was staggering, equivalent to the sun's total output over several days unleashed in a blink. Initially, the scientific community scrambled for answers. Some theorized that advanced civilizations might be harnessing the pulsar's energy, perhaps using it as a power source or even a beacon. After all, neutron stars are nature's perfect cosmic clocks, and their precision makes them intriguing targets for hypothetical engineers. But as tantalizing as this idea was, further analysis pointed to a more natural, though no less fascinating, explanation. The leading hypothesis now suggests these bursts stem from supercharged particles trapped in the pulsar's intense magnetic field. When these particles collide or reconfigure, they could unleash unimaginable energy like a cosmic short circuit. Supporting this view, researchers noted similar, though less extreme, behavior in other pulsars. The crab's unique environment, a chaotic mix of magnetic fields and high-speed particles, creates perfect conditions for such explosive releases. Even so, the exact mechanism remains unclear. Could it be magnetic reconnection where field lines snap and realign, or perhaps avalanches of particles cascading through the nebula? What's certain is that these pulses aren't just random noise. They're a window into the extreme physics governing neutron stars. The implications stretch far beyond the Crab Nebula. If we can decode these bursts, we might unlock secrets about how pulsars accelerate particles to near-light speeds, a process that could reshape our understanding of cosmic rays and high-energy astrophysics. Future telescopes like the upcoming Cherenkov Telescope Array aim to capture these fleeting events in unprecedented detail, potentially settling the debate. So while the allure of alien megastructures fades, the real story is no less thrilling. The Crab Nebula reminds us that the universe is brimming with natural wonders so extraordinary, they blur the line between science and science fiction. And as we'll see next, even the smallest cosmic players like the hardy tardigrades surviving in space hold surprises that challenge our notions of life's limits. Now, let's turn our attention to a cosmic contradiction that could redefine where we search for life, the so-called red dwarf paradox. These small, dim stars, which make up nearly 3 out of every 4 stars in our galaxy, should be ideal hosts for life. They burn so slowly that they can shine for trillions of years, offering planets in their habitable zones unimaginably long timelines for life to emerge and evolve. Yet there's a catch. Red dwarfs are also notorious for their violent tantrums. Take Proxima Centauri, the closest star to our Sun and a classic red dwarf. Its habitable zone planet, Proxima b, orbits so close that a single stellar flare could blast it with radiation levels thousands of times stronger than anything Earth has ever experienced. These flares aren't rare events, they're frequent and ferocious, often stripping atmospheres and bathing surfaces in deadly X-rays and ultraviolet light. For years, scientists assumed this meant red dwarf systems were cosmic dead zones, their planets scorched and sterile before life could even take root. But nature, as always, has a way of surprising us. Here's the paradox: while red dwarfs seem hellish, some organisms on Earth thrive in conditions we once thought lethal. Take Deinococcus radiodurans, a bacterium that can withstand radiation doses 1,000 times stronger than what would kill a human, or certain lichens and tardigrades which survive the vacuum of space and extreme UV exposure. If life can endure such extremes here, why not on a red dwarf's world? Astrobiologists now speculate that life might find refuge in unexpected places. Subsurface oceans, like those on Europa, could shield microbes from flares. Thick atmospheres or global ice sheets might diffuse radiation, while nocturnal organisms could evolve to only stir during their star's rare quiet periods. There's even evidence that some red dwarfs calm down as they age, offering quieter eras where life could gain a foothold. The James Webb Space Telescope is already probing these possibilities. By analyzing the atmospheres of red dwarf planets like TRAPPIST-1 siblings, it could detect gases like oxygen or methane, hints that life, against all odds, has found a way. The implications are staggering. If life can persist in these hostile systems, the galaxy's habitable real estate might be far larger than we ever imagined. So, while red dwarfs pose a challenge, they also expand our imagination. they force us to ask, is life rarer than we hoped or far more resilient than we dared to dream? The answer could lie in the next flicker of light from one of these tiny, tempestuous stars. Now, let's dive into one of the most debated chapters in the hunt for alien worlds, the Gliese 581g controversy. This story begins with excitement and ends with a humbling lesson about the complexities of spotting life-friendly planets beyond our solar system. Back in 2010, astronomers announced the discovery of Gliese 581g, a planet orbiting within the habitable zone of its red dwarf star. It was quickly nicknamed the Goldilocks planet, not too hot, not too cold, but just right for liquid water and maybe even life. Headlines roared with the possibility of the first confirmed Earth-like world outside our solar system. But science, as it often does, had other plans. Other research teams began scrutinizing the data, and doubts emerged. The planet's detection relied heavily on a method called radial velocity, which measures the tiny wobbles a planet's gravity induces in its star. Some scientists argued that these wobbles could have been misinterpreted. Perhaps they were caused by the star's own activity, like flares or sunspots, rather than an orbiting planet. The debate grew so heated that one astronomer famously declared, "I would not bet my spouse's life or even a small amount of money on the existence of this planet." The controversy highlights a broader challenge in exoplanet research. Even with cutting-edge technology confirming a world's existence, let alone its habitability, is incredibly tough. Gliese 581g, if it exists, would be a rocky planet about 3 to 4 times Earth's mass, with a likely tidally locked orbit, meaning one side eternally faces its star while the other remains in darkness. Yet, despite these intriguing details, the planet's status remains unresolved. Some studies still suggest it might be real, while others dismiss it as noise in the data. This uncertainty isn't just academic, it reshapes how we approach future discoveries. The Gliese 581g debate taught astronomers to be more cautious with bold claims, emphasizing the need for multiple independent observations before declaring a planet habitable. It also underscores why missions like the James Webb Space Telescope are so critical. By analyzing starlight filtering through exoplanet atmospheres, Webb can search for chemical fingerprints of life, offering a more direct way to assess habitability. So, what's the takeaway? Gliese 581g, whether real or not, reminds us that the search for alien Earths is a marathon, not a sprint. Every disputed planet sharpens our tools and refines our questions, bringing us closer to the day when we can confidently say, we're not alone. And until then, the mystery of Gliese 581g stands as a testament to both the ambition and the humility of modern astronomy. Moving beyond the mysteries of distant exoplanets, let's venture into one of the most mind-bending ideas in astrobiology, the possibility of life thriving near black holes. Yes, you heard that right. While black holes are often seen as cosmic destroyers, some scientists speculate they could actually power life in ways we've never imagined. At the heart of this theory is Hawking radiation, the faint glow of particles predicted to escape from a black hole's edges due to quantum effects. Though this radiation is incredibly weak for massive black holes, smaller ones, known as primordial black holes, could emit enough energy to theoretically support life. Imagine a planet orbiting at just the right distance, bathing in this eerie glow. Instead of sunlight, organisms might evolve to harness Hawking radiation, turning it into a bizarre form of photosynthesis. It's a scenario straight out of science fiction, but it pushes the boundaries of what we consider habitable. Of course, the challenges are staggering. Black holes are notorious for their extreme tidal forces, which could tear planets apart. Radiation levels would also be lethal unless life forms developed unprecedented shielding or biological adaptations. Critics argue that even if such a planet existed, the energy from Hawking radiation would be too sparse and chaotic to sustain complex ecosystems. plus primordial black holes, if they even exist, are hypothetical, never conclusively observed. Yet, the idea isn't just wild speculation. It forces us to rethink the very definition of habitability. On Earth, we've found microbes thriving in nuclear reactors and boiling acid, proving life can adapt to seemingly impossible conditions. If organisms can survive there, why not near a black hole? Theorists suggest that advanced civilizations might even engineer habitats around black holes, using them as cosmic power plants. This concept also ties into the search for technosignatures. If a civilization were tapping into Hawking radiation, could we detect the unnatural glow or energy patterns? It's a long shot, but it expands the toolkit for astrobiologists scanning the skies for signs of intelligence. So, while the black hole biosignature idea remains on the fringe, it serves a vital purpose, stretching our imagination. In the quest to find life, we can't afford to limit ourselves to Earth-like conditions. The universe is stranger than we know, and sometimes the most outlandish theories remind us to keep looking and questioning everything. Up next, we'll tackle another puzzle. Why haven't we found clear technosignatures from advanced civilizations? The answers might surprise you. Now, let's turn our attention to one of the most puzzling questions in the search for extraterrestrial intelligence. Why haven't we found any clear technosignatures? Despite decades of scanning the cosmos, the silence is deafening. But before we jump to conclusions, it's worth examining whether we've been looking in the right places, or if our assumptions about alien technology might be completely off the mark. For decades, the primary focus of SETI, the search for extraterrestrial intelligence, has been radio signals. The logic seemed sound. If advanced civilizations exist, they might use radio waves for communication, just as we once did. But what if that's an outdated assumption? Radio might be a primitive technology to a society far older than ours. Imagine humans 1,000 years from now. Would they still rely on radio? Or would they have moved on to something far more advanced, like quantum communication or neutrino-based signaling? Our searchers might be tuning into the cosmic equivalent of a dial-up internet signal in an age of fiber optics. Then there's the possibility that we're simply not recognizing the signs. Think about how much human technology has changed in just the past century. Extraterrestrial tech could be so advanced that it operates on principles we haven't even discovered yet. Some scientists suggest looking for Dyson swarms, vast arrays of energy-collecting structures built around stars to harness their power. These megastructures would absorb starlight, creating unusual infrared signatures. While we've spotted a few candidate stars with strange dimming patterns like Tabby's star, none have yet provided definitive proof. Another intriguing avenue is the search for artifacts within our own solar system. If an advanced civilization ever visited or sent probes, traces might still linger. The interstellar objects Oumuamua and Borisov sparked speculation, but natural explanations prevailed. Still, the idea isn't far-fetched. Upcoming missions to study asteroids and comets could inadvertently stumble upon something artificial. The challenge is also one of scale. The universe is unimaginably vast, and even if millions of civilizations exist, they might be separated by such immense distances that their signals haven't reached us yet, or are too faint to detect. Add to that the possibility that advanced societies might deliberately avoid broadcasting their presence, adhering to a cosmic version of the dark forest hypothesis, where silence is a survival strategy. So, where does that leave us? The absence of evidence isn't evidence of absence. New tools like the James Webb Space Telescope and next-generation radio arrays are expanding our search beyond traditional methods. Maybe the technosignatures we're seeking aren't radio waves or megastructures, but something entirely unexpected: anomalies in gravitational waves, quantum entanglement patterns, or even engineered black holes. The search continues, driven by the thrilling possibility that the next big discovery could rewrite our understanding of intelligence in the cosmos. And with that, we've reached the end of our journey through 30 groundbreaking cosmic discoveries, each a tantalizing clue in humanity's greatest mystery. Are we alone? Let's recap the highlights and look ahead to the missions that might finally provide answers. As we wrap up this cosmic journey, let's take a moment to reflect on the 30 extraordinary discoveries we've explored, each one a puzzle piece in humanity's grand quest to answer the age-old question, are we alone? From the tantalizing whiff of phosphine in Venus's clouds to the hidden oceans of Europa and Enceladus, from the enigmatic methane spikes on Mars to the water-rich atmospheres of distant exoplanets like K218b, every finding has reshaped our understanding of where and how life might thrive. We've marveled at interstellar visitors like Oumuamua, debated the mysteries of Tabby's star, and pondered the eerie silence behind the Fermi paradox. Whether it's the resilience of tardigrades in space or the wild theories about life around black holes, each discovery stretches our imagination and challenges us to think bigger. The beauty of this search lies in its unpredictability. Just when we think we've figured out the rules, the universe throws us a curveball, a repeating fast radio burst, a disputed Goldilocks planet, or a star that dims in ways we can't explain. But that's what makes science so thrilling. Every unanswered question is an invitation to dig deeper, to build better tools, and to keep looking up. And the best part, the next chapter of this story is already being written. Missions like the Europa Clipper will probe the icy moon's hidden ocean for signs of life, while the James Webb Space Telescope continues to decode the atmospheres of distant worlds. The Dragonfly rotorcraft will soar through Titan's methane skies, and new radio telescopes will listen for whispers of intelligence we might have missed. Who knows, the breakthrough that finally proves we're not alone could be just around the corner. So, what's your take on all this? Which of these 30 discoveries sparks your curiosity the most? Do you think microbial life is hiding in the clouds of Venus, or are you betting on the oceans of Europa? Maybe you're fascinated by the idea of Dyson swarms or hold out hope for a signal from Proxima Centauri. Drop your thoughts in the comments below. Let's keep this conversation going. Before you go, don't forget to hit that like button if you enjoyed this cosmic deep dive, and subscribe so you won't miss the next big revelation in our search for life beyond Earth. Turn on notifications too, because when humanity finally finds proof of extraterrestrial life, you'll want to be the first to know. Thanks for joining me on this adventure through the stars. Stay curious and keep looking up.